Now let's take a look at the molecule of formaldehyde we have here in the screen. If I want to figure out the molecular shape of this structure, I first need to figure out what is the steric number, which I do by looking at the central atom, how many bonds, how many lone pairs I have associated with that central atom. In this case, I have two single bonds and one double bond. In other words, my steric number would be 3. I also know that there is a hybridization, right? 1, 2, 3 places, so I would have an sp2 hybridized orbital. And when I have that scenario, I can predict that I will have a trigonal planar electron group geometry. I can also tell that because the three atoms surrounding that carbon are not the same, I would expect a little bit of a difference in that angle separation. Now, there is no expectation for you to memorize any of these specific angles. I do expect you to know the trends. Will a lone pair have a bigger effect than a bonding pair? Things of that nature. But the exact number, the exact degrees of separation, not really. Realize that the carbon atom in formaldehyde is sp2 hybridized. The three bonds are made with sp2 orbitals, and the unhybridized p orbital remains empty. When you look at carbon dioxide, in this case, you have a steric number of 2 double bonds. The geometry will be linear, and the atom will be sp hybridized because you only need two bonds between carbon and each of the oxygen atoms. Now, when we look at having different types of atoms, we have to look at the electronegativity associated with each of them, mostly because when you have differences in electronegativity, you may get polar bonds, you may even get ionic bonds, and these will dictate a lot of the physical properties that we see in organic and in inorganic molecules. Properties such as melting point, boiling points, solubility, etc. When we look at induction, that means the shifting of electrons within an orbital, how they move. This results in what we call a dipole moment, a difference in charge. And between plus and minus, more electrons will be minus, less electrons will be plus. Dipole moment, the amount of a partial charge times the distance of that partial separation. Now, this doesn't mean that they hold actual charges. It means that the electron distribution is not even, and it creates a little bit of a dipole, slightly negative, slightly positive poles. Dipole moments are usually reported in units that we call debye. These are very common in most of science, really. For molecules with multiple polar bonds, the dipole moment is the vector sum of all the individual bond dipoles. So for instance here, we have this molecule, carbon-chlorine. Chlorine is more electronegative, so it pulls towards itself. And when you look at these two vectors, the sum of them will be somewhere along this area, which is where you get the molecular dipole moment, making it a polar molecule. Same is true for ammonia. The actual vector is more towards the lone pairs than anything else. Now, before you can tell whether something is polar or not, you have to be able to tell what is the geometry of the molecule. So using the Lewis dot structures are not going to be enough for you to figure out whether something is polar or not in most cases. So ideally, we will be practicing VESPER before we assign polarity or non-polarity, etc. These are some of the common solvents we use in the organic chemistry lab and their dipole moments. As you can see, we go from 0 debye, these are non-polar solvents, all the way to highly polar solvents such as acetone. That dipole moment will give us an idea of which is more polar, which is less polar, and from there we can decide how we're going to dissolve a specific compound based on any given set of conditions. Now let's talk a little bit about intermolecular forces and how they play a role in physical properties. Many properties such as solubility, boiling point, density, state of matter, melting point, just to name a few, are affected by attractions between separate molecules. Neutral molecules are attracted to one another through a series of what we call intermolecular forces, dipole-dipole interactions, hydrogen bonding, and dispersion forces. When we look at dipole forces, they result when polar molecules line up with regards to their charges. So the plus and the minus, they sort of attract each other, and they line up based on that attraction. They're not going to bind, they're just going to feel an attraction, which makes them sort of line up or organize so that it maximizes that attraction, making them more stable than if they didn't have that attraction. Acetone's permanent dipole results from the difference in electronegativity between carbon and oxygen, which we kind of saw already. The dipole-dipole attractions between acetone molecules increases its boiling point and its melting point. And we can see this because when you have a similar molecule, say molecular weight, no dipole, the boiling point is actually much lower. That means that they don't really interact with each other too much. They just go into the gas phase. We actually have here some numbers. If you're interested, isobutylene and acetone, polar versus non-polar. Acetone has a boiling point of 56 degrees Celsius, whereas isobutylene has a negative 7 degrees Celsius. So there's a pretty large difference between them. And this all stems from that intermolecular force at dipole. Hydrogen bonds are notoriously strong among the intermolecular forces. They're a type of dipole-dipole attractions, and they happen between hydrogen and a highly electronegative atom bound together, and then another electronegative atom generating that attraction. Hydrogen bonding is the attractive force between a hydrogen bonded to an electronegative atom and a lone pair on another electronegative atom. This is usually associated with nitrogen, oxygen, and fluorine. Only when hydrogen shares electrons with a highly electronegative atom will this actually happen. So hydrogen isn't going to hydrogen bond just because it's there. So if it's bound to carbon, for instance, then it won't hydrogen bond. Increasing the amount and extent of hydrogen bonding explains why the following isomers have different boiling points. So you see here, triethylamine, ethylamine, and propylamine. You go from 3.5 degrees Celsius all the way to 49 degrees Celsius. That's because you have no hydrogen bond here, one opportunity to hydrogen bond, two opportunities to hydrogen bond. That makes a pretty large difference actually. Hydrogen bonds are among one of the most important forces that cause the DNA to form a double helix and many proteins really to fall into an alpha helix. Other forces will be your London dispersion forces. If molecules are nonpolar, then they don't get hydrogen bonds, they don't get dipoles, but they still have London dispersion forces. And this happens when you have that electron cloud, it sort of shifts, it moves, and when it does, then it creates a temporary, very short-lived dipole. And that dipole will incite other dipoles to form, and so on and so forth, kind of like a wave almost. And that constant random motion will generate these interactions that are considered the weakest of the intermolecular forces. The constant random motion of the electrons in the molecule will sometimes produce an electron distribution, kind of like what we see here in this drawing. Electrons moved a little bit more here, so it's a little bit uneven, slightly negative charge. This will induce a slightly positive charge on its neighbor, and so on and so forth. Such fleeting attractions are generally weak. In fact, as I mentioned before, out of all the intermolecular forces, London dispersion forces are considered the weakest, but they still account for some of the energy associated with having to boil or melt some of these compounds. So they require energy to be dissociated, and we know because when you take the gas phase of this compound, you notice that its energy is a little bit smaller than if it were in liquid form. So that means that if you give it a chance to interact, it will interact in this London dispersion force type interaction, and it increases the stability, which is convenient for the molecules. Some of the general characteristics: the greater the surface area of a molecule, the more temporary dipole attractions are possible. Consider the feet of geckos. This is an actual example. They have many flexible hairs on their feet that maximize surface contact. And these, being nonpolar, they actually have London dispersion forces. They're strong enough to support the weight of a gecko. But this is assuming you have a ridiculously large amount of surface area, which they do on their feet. That's why they have these flexible hairs. This is why molecules with more mass are generally they generally associate a higher boiling point than if you were a smaller one. You can see butane, boiling point 0 degrees, versus hexane, which is actually a liquid almost at room temperature. Uh, 69 degrees Celsius. It actually is pretty warm. You need to heat it up quite a bit um, for it to boil off. Now, branching also plays a role when we look at um, intermolecular forces. The more branching in a molecule, the lower its surface area, and the weaker the London dispersion forces. And we can see here just one branching, two branching, and no branching at all. And you can see the difference in boiling points. Now, let's talk a little bit about how all of this translates into actual physical phenomena that we see in the lab. Um, from your general chemistry, you probably learned something, one of our tenets, which is like dissolves like. What that usually means is that polar solvents interact really well, they mix really well with polar compounds, and then nonpolar with other nonpolars. If the compounds mixing are all capable of hydrogen bonding and or strong dipole interactions, then they mix really well actually. And when they don't, they only have long non-dispersion forces, then they mix with other non-polar compounds. That's pretty much what it is. We know it is difficult to get a polar compound to mix with a non-polar. Um, so usually when we need something polar to interact with something non-polar, and here we bring the example of like dirt on plates, like grease, things of that nature, oil, then we use molecules that we call soap. Some molecules are also known as they form micelles, which means that you have polar and non-polar components within the same molecule. The polar component will interact with the water or the solvent, right? In this case, because it's, let's say, soap, then it's water. Water will interact with the polar sides, and then the grease will interact with the non-polar, and it generates this bubble or this sphere, right? That's how you maximize that area, make it the most efficient. And once you're trapped in that structure, then you move away, right? That's how you clean, no? And lastly, one of the most important applications that we'll see with regards to intermolecular forces, VESPER, and all of these topics that we will discuss in this chapter comes from drug receptor interactions. When we look at a specific drug, we're designing drugs or any type of pharmaceutical compound, we need for it to interact with a very specific receptor. So we analyze its structure, if it's polar, if it's a large molecule, if it has high capability for hydrogen bonding, all these things, they go into the design of drug receptor interactions.